Welcome back, everyone. Let's continue our journey together for the NPTEL course Computational Process Design. I am Dr. Hariprasad Kodamana, and now we would go through the concept called geometric methods for reactor network synthesis. Okay, so before we go on to the details of geometric methods for reactor network synthesis, let's check what are the key resources that we would be using in this part of the course content. The key resource here is the reference one, which is Biegler, written by Biegler, Grossman, and Westerberg, Systematic Method for Chemical Process Design, and to some extent the reference number 2, Douglas J, Conceptual Design of Chemical Processes. So, so these would be the key resources in this part of the course content. So, maybe let us just recap what we have done in the last 2-3 lectures. So, we were trying to design what we call as the heat exchanger network synthesis. So, from the heat exchanger network, now we are going to the next level of equipment, which is the chemical process reactor. So, in heat exchanger network design, just to recap, since this is all part of the network synthesis. So, we have learned about various modes of heat transfer, we have learned about heat transfer resistance, and we have learned about overall heat transfer coefficient and other related concepts. We talked about the types of heat exchangers, design of, specifically we were looked at the design of shell and tube heat exchangers, and we were looking at a concept called heat duty, which is the amount of heat to be transferred, and what is the concept known as logarithmic mean temperature, and heat transfer coefficient, flow management. For instance, what is the type of flow that you should use, cross flow, counter flow, parallel flow, so on and so forth. Then we went ahead and looked at a concept of pairing the process streams using Cp values to determine what is the minimum delta T, which we call it as delta T minimum, and that is the key aspect in the design of heat exchangers. Further to that, once that was done, then we went ahead and looked at what is the pinch analysis. Pinch analysis, of course, a crucial part of the heat exchanger network design. The pinch point, of course, represents a critical temperature point in the system where the smallest temperature difference between hot and cold stream occurs. So, controlling the pinch point is an essential thing rather in the design of heat exchangers. Then once we have learned what is the pinch point, then we actually looked at two different cases, a case which is called below pinch and a case which is called above pinch, wherein you see that the Cp of Cph is greater than Cpc, in other case Cpc is greater than Cph. So, once that was done, and finally we went ahead and did a pairing of hot stream and cold stream by means of tick-off heuristics. So, tick-off heuristics helps you to minimize the requirement of total number of heat exchanger unit by utilizing the maximum possible heat transfer between paired fluids. They would help you to connect the process streams that would lead to maximum heat recovery. So, once that is done, a process design of heat exchangers can be completed. So, the next part, while continuing heat exchanger networks, we will now look at chemical process reactors. So, some of these concepts possibly would have been known to you by means of your chemical reaction engineering course, but here we entirely focus on how do we find out the volume of the reactor, okay, by means of geometric methods. We will look at some of the concept that you may know earlier to find out to compute the volume of three specific reactors as we see over here, which is well mixed batch reactor, a continuously stirred tank reactor or continuous stirred tank reactor people will call, which is CSTR, and a plug flow reactor. So, in batch reactor, your feed and the desired components are charged in the reactor directly. Okay, then the reactor is of course a closed vessel and the reaction would takes place, and once a specified time is completed, which assuming that the reaction has been completely taken place, you open up the reactor, okay, and take out the products. So, you would there would be a stirrer inside, that's why we call it as well mixed batch reactor. And you are typically not loading your feed or continuously, or not extracting the feed continuously. On the other hand, continuous stirred tank reactor, as you know, you have a provision to have continuous feed and continuous output. And unlike batch reactor, the product from this continuous stirred tank reactor is always can be extracted in a continuous fashion. The next is plug flow reactor. In plug flow reactor, your fluid stream would move axially until it get out at the other end of the reactor. Till that time, the desired conversion would have taken place. So, these are the three reactors that we are specifically focusing on, and we may also look at a bit on the recycle reactor at a later time. But when we speak about a concept called attainable region, which is the key concept in the geometric design of reactor, we typically limit our analysis to CSTR and PFR. So, this is what is the agenda. So, let us look at the things in details. So, again we could just start with reactors. Reactors are chemical engineering vessels wherein the chemical reactions would take place and transform the raw material into desired product. See, when a reaction is taking place, we are essentially implicitly assuming that we are carefully managing the heat and mass transfer or energy and mass transfer, because the reaction would takes place. For a reaction to happen, a careful control of the energy and mass transfer is required. And further, further you also need to have a deeper understanding of kinetics, thermodynamics for a careful reactor design. And if you want, so reactor one is of course reactor design, and if you wanted to optimize the reaction condition and outcomes in a designed reactor. So, it is just not the heat and mass transfer, beyond which of course there is kinetics and also the thermodynamics. So, kinetics would detect the time and the thermodynamics would detect the direction. So, what are the key design considerations in designing in a reactor? Okay, so the design consideration include of course material and energy balances, and of course any reaction would possibly catalyzed by an entity called catalyst, which helps you to reduce the activation energy barrier. And you need to incorporate the catalyst for improved reaction rate. Not only for that, even improved selectivity. So, selectivity essentially mean that, let us say you have a, a desirable component and undesirable component, how you can isolate how the reactor is good in producing your desirable component with respect to the undesirable component. And further, a precise management of heat and mass transfer within the reaction environment. So, entire process would include all of this. So, if we will see some of, as I told, some of these concepts you are familiar as part of the reaction engineering course, but here our emphasis would be on just on the design aspects of it. For instance, how do you compute the reactor volume? Once the reactor volume is computed, basically you can design the vessel how much ever you want, how can you, and what is the particular combinations if there are alternatives possible. let's say if you can integrate the reactor network. So we are interested in reactor network synthesis. So can we, what is the combinations of, how do you combine CSTR and PFR, or even CSTR and CSTR, and so on and so forth. So the analysis would be typically limited to these aspects only. So let's again just go back to the basics to understand how the mole balance equation in the reactor works. Let's assume that we have a reactor here, 4 in, you have a molar flow of Fj naught going inside, and the reaction takes place. The reactor would and eventually, and you are taking out a molar flow rate of Fj. So now let's write the balance equation for the reactor. So you can see that. So let's say molar flow rate of J into the system. So J is the component, minus molar flow rate of J out to the system, input minus output. And the next part is the generation of J by the chemical reaction and consumption of J by chemical reactions. These are the 4 things that can happen inside the reactor. Your component is fed in, your component is moved out. There may be, as part of the reaction, there may be some generation of that particular compound, and there may be some consumption of that particular compound. And this would be balance of the rates of all of this would be the rate of accumulation of the jth component in the reactor. So let us denote Fj naught as the molar flow rate of J into the system, and Fj as the molar flow rate of J out to the system, and let us combine the generation and consumption term together as Gj. G is the uh, G is the total resultant of generation and consumption, and this Gj essentially indicate that this is for the jth component, and the rate of accumulation of the jth component in the reactor, let us denote as dNj by dt. And of course, your flow rate units are mole per second, okay, and the final accumulation would be of the unit of d by dt of mole. So, certain reactors you would see that the reaction rate is uniform across the volume, and certain reactors you would see that the reaction rate is non-uniform across the volume. In those conditions, your Gj would have 2 different structural form. Okay, if it is a non-uniform generation across the reactor, so you have to actually integrate that the rate across the entire volume. Okay. So Gj would be the integral of Rj times dV, because the generation is non-uniform, and this is, in most of the cases you assume it is a uniform reaction rate, then the Gj would be your reaction rate times V. And let's again just consolidate the units. Gj is the moles of J generated per unit time, and Rj, of course, the reaction rate would have, we will define it as moles of J generated per unit time and unit volume of the reactor, and V is the volume of the reactor. So that's why to get Gj, we will have to multiply your Rj times V, so that your moles generated per unit time can be the units of the moles generated per unit time can be recovered. So next, as a next step, so this moles balance equation, which is of course you would have if you would have learned in a chemical reaction engineering course, we would specifically look into the how do we apply for um, plug flow reactor, continuous state rank reactor, and of course batch reactor, and towards the end recycle reactor. So let's look at the batch reactor. In the batch reactor, the reactants are always placed as a starting. There is no more feeding happens intermediate. The reaction is allowed to proceed for some amount of time without the removal of product during the reaction. So you charge the reactor with the you charge the reactor with your reactants. Okay, then you close it, and you kind of allow the reaction to proceed for a long time or desired time, whatever is the batch time, what we call it as the batch time of the process. So unlike continuous other reactors, batch reactor operation is unsteady state. Why? Because the composition of the reactor is changing with time. As there is no feed inlet or feed outlet, you can see that as time progresses, your composition of the reactants and of course the products are changing with time, and eventually you stop the process. So, I, a batch reactor eventually operate under unsteady state conditions. And you have a stirrer in any in any reactor configuration for well mixing. So, under ideal condition, we would assume that a batch reactor is perfectly mixed. So, now let us trying to write the balance specific to the batch reactor, okay, assuming the concentration and temperature are spatially constant but not constant in time. So, this is very important. It is only spatially constant. Over the time, of course, it is varying. So, at a particular time spatially it may be constant, but over a period of time, as I told, when there are as the reactants are consumed and the products are formed, it is not constant in time. So, okay. So, what would happen is you have charged the reactor. So, there is nothing like Fj naught and Fij, either you are already charged it. So, what the remaining term that is there in your reactor equation would be integral Rj dV, which is corresponding to this particular term. So, which is corresponding to this particular term in a sense, which is equal to dnj by dt. So, so in short, if we want to summarize, we can say that the batch reactor design equation includes integral of Rj dV for the j component Rj dV, which is equal to dnj by dt. So, so we have made this point that the concentration and temperature are spatially constant. So, the reaction rate is also spatially constant, but of course, again as you would see, it is varying with respect to time. So, you can see that. So, let us summarize the ideal batch reactor design equation. So, when we Rj times V, so integral of Rj times dV is equal to dnj by dt. So, now if you do not assume a non-uniform rate, if you assume that the rate is specially constant, you may be able to integrate the dV separately by taking out the Rj. So, the eventual relation will be Rj times V is equal to dnj by dt, whereas of course, the V is of course the reaction mixture volume. So, we have done with batch reactor. So, let us move into the next type of reactor, which is of course the CSTR. So, CSTR as we have seen before is a continuous operating reactor. So, we continuously add reactants and also continuously remove products. So, it eventually behave like an open system, things are going inside, things are coming out. And so, what you can see that the inlet stream is instantaneously mixed with the bulk of the reactor. So, once you are inside the reactor, when a feed is just inside the reactor, it mixes instantaneously. And ideal CSTR, of course, based on a stirrer that we provide, we assume that the mixing occurs very well. And as a result, and there is temperature and concentration are fairly uniform throughout the entire space. So, under ideal case, it is completely uniform throughout the space. And whatever you take out of the reactor, which we call it as the exit stream, and the composition of the exit stream is the same as that of the reactor. What is that inside the reactor? So, Ca outlet, which is of course the outlet composition, which is of course which is equal to Ca tank. So, what is inside the tank, and that is what you are draining out. Fine, since there are constant inlet and constant outlet, there is a possibility, so you can or rather the reaction eventually reach at a steady state, and the reaction rate would be the same at every point, and later it will not change with respect to time, because when things become when things are in the steady state condition, you may be able to see that the reaction rate is same and at every point, and it is not changing with respect to time. So again, let's say go back and revisit our design equation, fundamental reactor design equation. So you may see that your Fj naught and Fj are non-zero here. Why? Because you have a continuous feed in and continuous extraction of the product, and integral Rj dV would be remain, and what is going to be 0 is dnj by dt due to the steady state conditions. So a CSTR steady state equation, design equation, can be simplified as Fj naught minus Fj plus Rj times dV is equal to 0. Fine. And further, and if for an ideal reactor, ideal CSTR reactor, the temperature and concentration are also constant. So the reaction rate is again specially constant. So you could just decouple Rj and dV as we did in the previous time. So what would happen here? Your dV would be integrated to the full reactor volume V, and the simplified reactor equation would be V, which is the volume of the reactor, which is what we need to design the system. V is equal to Fj naught minus Fj divided by minus Rj, because the stem goes to the right hand side. Fine. So there are so we can also rewrite this as a function of minus Rj. So in that case, minus Rj uh, uh, would be Fj naught minus Fj by V, which is further you could replace in terms of the concentration of the species. So if the inlet concentration minus outlet concentration, assuming a common volumetric flow rate. Okay, so you can write V times Cj naught minus Cg, and this V by capital V, which is the volume of the reactor, divided by the volumetric flow rate, we actually replace by a term called space time of the reactor, or residence time of the reactor. So this is also one way of representing the design reactor equation, which is essentially in terms of concentration and the residence time tau, and which this is directly in terms of the volume and the rate and the molar flow rate. So either of these we will be able to use it, and we see that this particular relation we tend to use it at a later time, wherein we trying to do the attainable region design. So this part, so let's reserve it for now. Let's look into this. We will get back to this particular relation when we go till the attainable region. And the third type of reactor is the plug flow reactor. It is also called a tubular reactor. And what specific in this case is the reactants are consumed as they flow through the reactor. So you can see the reactants are consumed as they flow down through the length of the reactor, and finally you will get your output. And to do this analysis of, or rather to do a balance of PFR, okay, you will have to take an elemental volume, because over you will have to define a small dV over which the reactor design equation hold, and you finally integrate. And again, like our CSTR, PFR is also operated at steady state, and the key aspect is no radial variation. So no radial variation of temperature, concentration, or the reaction rate. Of course, it may vary axially. All fluid gas elements would have the same resistance time. So you can see that it is like a front that is moving from inlet until it reaches to the outlet. So let's rewrite the reactor equation back to the plug flow reactor. Okay, Fj naught. Okay, V. So let's say this particular part is V, and this dV is this small volume in which we are doing this balance, and so V plus dV would be the this particular point. So Fj naught at V minus Fj at V plus delta V would be Rj times delta V. Of course, under steady state condition, dnj by dt would be vanished. And what we would see here is that, so see Fj naught minus Fj naught at V minus Fj naught at V plus delta V, when we divide it by delta V plus the remaining term would be Rj tend to 0. And we will have to do this a case when your dV is tending to 0, which essentially means that your delta V tend to 0. When we start applying the limits, okay, you can see that this particular term would be written as dfj by dv, and in fact it would be minus dfj by dv, because it is v plus delta v, and when we take your rj that side it will be minus rj, and we balance the signs, it would be dfj by dv is equal to rj. So, this is the ideal steady state PFR design equation. So, we have done. So, see again, our aim is to write the design equation, and wherein we have the key component. So, we are interested in identifying the volume, and which of course has a function of the flow rates and the rate which drives the kinetics of the process. So, we have done it for PFR, and let us do a comparison of all three before we move to the next case. So, for selecting the reactor, we have to use certain what you call heuristics or thumb rules. If it is small scale production, batch reactor is favored, because you can charge it and leave it for waiting. And of course, production of expensive products. So, if you because if you want to have tighter control, and you are using a smaller scale production, batch reactors of course is favored, and high labor cost per production per batch. And why it is so? So, somebody has to charge the reactor. Once the production is done, you will have to remove it, okay, then clean it up and make it ready for the next charging for the next batch. As a result, the process being discontinuous, okay, so somebody will have to, there would be a lot of manual labor needed to uh, do various intermediate steps. So, as a result, the labor cost would be high, and of course, it is not really used for large scale production. Large scale, you need to get your products continuously at every point of time. So, in this case, this is going to be slightly difficult. In fact, it is going to be very difficult. So, now look at the second case as we know. So, you can see that in CSTR, it is typically used for most homogeneous liquid phase flow, okay, and intense agitation you need to so there is an assumption that's stated saying that every point in the reactor your it's well mixed, right. So, as a result, you need to you need an intense agitation inside the vessel, and it is fairly easy to maintain and good temperature control. Why? Because it is well mixed. There is no isolated temperature spots that would eventually lead to certain runaway reaction. But the key difficulty, or rather the key thing that we need to note here, the conversion of reactant per volume of reactor is the smallest of the flow reactors. Its very large reactor are necessarily to obtain high curves. So, as a result, very large reactors are necessary if you need to obtain high conversions. So, now go to the third the reactor as we seen PFR. So, it is an so see CSTR is most homogeneous liquid phase, in PFR it is most homogeneous gas phase. Fine, it is if relatively easy to maintain, usually produces highest conversion per reactor volume for in any of the flow reactors. I am sorry. And so the key, so the difficulty, so there is no like agitation or well mixing happening in the PFR, as so the reaction happens when a front moves from inlet to the outlet. So, as a result, the temperature control within the reactor is not easy. There is no means in which you will be able to do a a good temperature control. As a result, hot spot can occur inside the reactor. So, now that we have learned about the design equation, let us try sizing the reactor. So, all our design equation that we learned, when we are specifically interested in the geometric design, essentially mean that you look at it, so the process was done graphically, okay. So our governing equations for CSTR and PFRs. So we would now focus more on to the CSTR and PFRs. Okay. So it has volume as a variable. So we would now try to see how it could be computed. Once you have the volume, you can of course design the. So the key variable in a design is volume. So if you know the volume, you can make the vessel as per your wish. So let's go back and see how this could be done. So the volume of the CSTR required to achieve a specific conversion can be obtained if you know how the reaction rate depending upon the conversion. So what we have to do is we need to identify the reaction rate as a conversion. So we know the ideal steady state CSTR design equation, okay, and which is of course a function of volume. Volume of the CSTR is equal to F naught minus FA divided by RA, and now we replace F naught as a function of XA. So F naught FA would be FA naught into 1 minus XA. So when we simplify them together, it would be FA naught into XA minus divided by minus RA. So now what you can see here, you can see there are two terms product. So you could decompose this particular function as the product of FA naught by minus RA times XA. So the volume is a product of FA naught times minus RA and XA. And to design this reactor geometrically, what we need to do is to go and develop a plot which is known as Levin-Spale plot. So Levin-Spale plot is a plot that relates between FA naught minus RA and XA. So when we plot it, okay, and you could see that eventually you would it would result in a curve, but you can see the volume of the reactor once you have it is a product of FA naught by minus RA and times XA. So volume of the CSTR is a very you could just extract it as a very volume of the is just this particular rectangle, because this part is FA naught by minus RA and this part is XA. So VSCSTR is a rectangle with a base XA with a height of FA naught by RA. So you can just evaluate this particular area. So this is fairly easy if you look at this in terms of geometrically, and by employing Levin-Spale plot, which is a function which is plotted as a function of FA naught by minus RA times XA. Fine. So now let us look at sizing the PFR. So the volume of the PFR required to achieve a specific conversion can be obtained if we know how the reaction rate, again depending upon the conversion XA. So let's go back and look at the ideal PFR design equation, which is VPFR. Again, it is an integral of FA naught to FA at exit, in integral of that or dFA by my RA. So you may be able to again FA naught, FA we can rewrite as a function of FA naught, fine. So FA naught times 1 minus XA. So you can take the FA naught out and the differential term would be replaced by dFA to dXA, because the variable is changed, and there would be a minus sign here, and you see that the integral is also replaced. So previously the variable was df, now it is dx. So you see that at the start of the reactor the conversion is 0, and the exit you kind of achieved a conversion of XA, and the integral is updated appropriately. Again, let's plot the this particular curve FA naught by minus RA and XA. So you would eventually result in a curve like this, since this is an integral. So integral typically evaluated as an area under the curve. So once you have the plot available, plot of FA naught minus RA versus XA, volume of the PFR is the area under the curve. of Fa naught by minus Ra versus Xa at Xz. So, this particular curve, whatever you plot, and the area under the curve, because integral is evaluated always as an area under the curve. So, we are now done with computing the volume of the PFR. So, now let us look at certain combinations. So, which essentially means that you can have a CSTR and PFR in series, a CSTR in series. So, let us look at how we do the combination study. So, because we are trying to design the network. So, network essentially means that there are more than one component and not any standalone reactor is there in the picture. So, now let us look at the case where we have more than one reactor. So, and also they are connected in series, essentially mean that one reactor output is going to the next reactor inlet and so on and so forth. So, when reactors are in series, exit stream of the one reactor enters in the next reactor as an inlet stream. Okay. And if there are no side stream, which essentially means that you are not taking any tapping from any particular stream, the conversion at a point I let be an arbitrary number, which is of course xi, you can define that as the total moles of A reacted up to the point I divided by the moles of F fed into the first reactor. So, wherever you have completed, so your moles are reacted, how much is total mole reacted up to the point I divided by the moles of F fed into the reactor. So, now let us take a simple reactor in series for illustration. So, here you have 3 reactors, a CSTR, a PFR followed by a CSTR. So, Fa naught is coming in, okay, it particularly has a volume V1 and Fa1 is going out. In this case, your I is 1 because this is the ith first pass and the conversion is x1, then it is going to in the next reactor, let us say having volume V2, output will become Fa2, and in this case now it is I2 because it is coming out of the second unit and having a conversion rate of x2, and it is going to the third reactor and it is going as and with an output of Fa3 and x3 where I index I become 3, and of every time you may be able to as Fai is equal to Fa naught minus Fa naught times xi. So, this is looking at this particular equation. At any point of time, Fai would be defined as Fa naught by Fa naught times xi, where xi is defined by this particular relation. So, now let us look at 2-3 combinations. One is of course reactors in series. So, in this case you have a 2 CSTRs connected in series, Fa naught coming in, it is having a volume E1, Fa1 and having a conversion x1 going to the reactor 2 having volume 2 and it is going out as Fa2 with an index I2 and x2. So, we will be able to write the volume expression or a CSTR descent relation for individual reactors. V1 is equal to Fa naught minus Fa1 divided by minus Ra negative of neg Ra1, and what is Fa1 as per the relation Fa naught into Fa naught times x1, and you will be able to evaluate now V1 as Fa naught substituting Fa naught over here, this would be Fa naught minus Ra1 times x1. So, now look at the second case, which is the second reactor V2 Fa1 minus Fa2 by minus Ra2. Okay, again looking at the relation Fa2 is Fa naught minus Fa naught times x2. Fine. Now, we have to replace Fa. So, when we are replacing Fa naught with this expression and F1 Fa1 with this expression, we may see that the final expression of V2 would be Fa naught divided by minus Ra2 times x2 minus x1. So, you have to replace Fa2 with this particular expression and Fa1 with this particular expression. Fine. So, we have our V2 over here. So, now how do we compute the total volume for a if the conversion is happened up till x2. So we know that we again need to go back and plot Fa naught by Ra times x, right. So up till the reactor 1 conversion, it would be x1, and further to that it would be x2. So this is the conversion of A, and as per the Levin-Speed plot, we can see that the area of this particular box would be equal to the volume V1, and this particular volume would be equal to V2. This is the total volume, would be the summation of all of this. So this is what. So for the conversion that to happen, you may see that the volume 1 would occupy a would be computed as Fa naught minus Ra1 times x1, and in the second case, of course, Fa naught minus Ra2 times x2 minus x1, which is the base. So similarly, when we do a PFRs in series, okay, so you have a PFR having volume 1 connected to volume 2, Fa naught with a possibly a conversion already happened, x naught is coming inside. It would be it is going out as Fa1 and with a conversion x1, and eventually Fa2 and x2. So let us rewrite expressions independently for both these vessels. So here the V1 would be integral of Fa naught times integral Fa naught to Fa1 by dFA by Ra. Fine. So again Fa1 you may replace it as Fa naught by Fa naught times x1, okay, and finally dF is also replaced as uh, uh, so we will be able to write dF as a function of xa, then apply the differentials, the symbol relation would be become, and also updating the limits of the integral, it will become v1 times x naught times x1 Fa naught dxa by minus Ra. The same applies, the same process applies for the second reactor as well, V2. Okay. So here your integral should be from Fa1 to Fa2, integral is from Fa1 to Fa2 dFA by Ra, and Fa1 as it is Fa0 times Fa0 times x2 is your F2 and dFA by Ra, and you may replace dFA with expression as a function of xa, and Fa1 with Fa0 by x1. You may see that eventually the integral would stand from x1 to x2, because that is inlet conversion and this is outlet conversion, and V2 would be finally evaluated as integral x1 to x2 Fa0 dxa by Ra. So now let us look how this translates as the volume geometrically. So you can see this part of the curve wherein you see this is the xa, the plot is between Fa0 minus Ra with respect to xa, and let us assume that this is the point of x1 and this is x2. Area under this part of the curve would belonging to lead to the computation of V1, and the remaining part of this from x1 to x2 would resulting would the volume of V2. So now let us look at the combination of a CSTR and PFR together, wherein you have two options. First, you can have a CSTR followed by a PFR, or a PFR followed by a CSTR, but we may see that the volume of combination 1 and combination 2 are not going to be equal, which is of course be soon evident from the graphs below. So in the first case of when we start plotting Fa0 by minus Ra times x1, so the volume would be this particular area. The remaining part would be x1 times x2 Fa0 times dxa by Ra. Just recall our previous step, and this would be the area of the rectangle, while this would be area under the curve. Fine. In the second case, since your PFR is coming first, you can see the total volume. Your volume of the PFR would be area under the curve first, okay. Then you have a area of the triangle, that is rectangle, that is formed by the second reactor. So of course, this is done by plotting again Fa0 minus divided by minus Ra times xa, okay, with your first reactor conversion as x1 and the next final conversion as x2. So you can see that this is the key. So you can visually see that the total volume, which is of course the the area of the entire shaded regime would be different in case 1 and case 2. In one case it is of course going to be higher, and other case it is going to be lower, and it would critically depending upon the value of x2. Wherever you are marking your concentration, sorry, not x2, both x1 and x2, the conversions and independent individual conversion would dictate the total volume that is required to uh, so the total volume that would be used to design. So let's summarize some key points that we learned. For multiple reactions, we can generalize the behavior of power law kinetics considering reaction rate. That's always what we do. For process design, the preferred objective is frequently is selectivity and not the conversion. Why? Because and here the relative reaction order determines which reactor type is preferred. Selectivity is if there are multi-product reactions, how one product is outperforming the other one, preferred product versus the non-preferred product. This particular aspect is being represented by the term selectivity. So, eventually selectivity is slightly a better variable. For reactions in parallel, the concentration level of the reactant strongly influences the product distribution. Higher reaction concentration, higher reaction concentration favors the reaction of higher order, and a low concentration favors the reaction of lower order. For reactions in series, mixing of fluid of different compositions strongly influences the formation of an intermediate. So, you are considering a reaction wherein A going to C. So, the formation of the intermediate is strongly influenced by the mixing of the fluids of multiple different compositions. Maximum possible amount of intermediates is obtained if fluids of different compositions are not allowed to mix each in the network. And of course, you can also have a series parallel reaction, and you can analyze in terms of their constituent parallel and series reaction components for optimum contact and optimum further and leading to optimum sizing. And as we have learned before, temperature and pressure is a key variable in reaction. For reversible reactors, the maximum yield is obtained by maintaining the profile at the highest allowable temperature within a PFR. For reversible reaction in gas phase, an increase in pressure of course increases the conversion if the moles of the products are fewer than the moles of the reactants, and vice versa. So, if it is reversible, if you increase the pressure and if the moles, so the moles of the products are reduces, okay. So, it actually favors the conversion and vice versa. And reversible reaction, the equilibrium concentration rises with increasing temperature for endothermic reaction and falls for exothermic reaction. So, pressure and temperature act as key variable in terms of the driving force, driving the reactions. And typically a high temperature favors the reaction of high activation energy, and low temperature favors the reaction of lower activation energy. So, in addition to whatever we have mentioned, which is of course just based on the geometry, the hidden factors, so which is coming, which may play a role could be the effect of temperature and pressure. So, now let us look at another type of reactor which is known as a recycle reactor. So, in recycle reactor, what you may see here, you have a feed, and the feed, this is what we call it as a fresh feed, and it is getting mixed at a particular point which something known as recycle feed. We will speak about that. The reactor has happened, then the combined feed is going inside the reactor and it is going outside, and certain point you draw out the output and the remaining is allowed to recycle. This is the geometry or the architecture of the reactor. So, now let us understand FA naught is the molar flow rate of the fresh feed, V is the volumetric flow rate. At the moment there is no XA naught, XA naught is equal to 0. At the moment you are a stream having XA2 conversion mix up, the volumetric flow rate is here is R times Vf, and having a with FA3 having the molar flow rate, and eventually when it mixed up, You may be able to represent this as Fa naught prime because it is just a reconstituted Fa or a new variable Fa1 having V1 and Xa1 which is going out as R1 times Vf would be the volumetric flow rate with the conversion of Xa2. Why it is R1 times R1 plus 1 times Vs? Because you are taking out the final output is Vf and R times Vf is recycled back. So, this will be R1 times R plus 1 times Vf. XAF or XA2 you replace it as your final conversion. So, how to define the value of R, which is the recycle? Recycle is the volume of the fluid returned to the reactor entrance. Okay. So, volume of the fluid returned to the reactor entrance. So, here this is the reactor entrance and the volume of leaving the system. What is the fraction of the volume that is returned back compared to the volume leaving? And Fa naught which is here, it would be the way we define it as A which would enter in an unconverted recycle stream, which is this, plus A entering in fresh feed. So, how do we compute Fa naught prime? Okay, R times Fa naught, which is coming from here, and times Fa naught, it would be R1 times R plus 1 times Fa naught. Okay. So, let us do volume calculation. So, it would be V times. So, your integral would be from XA1 which is from here to XA2 which is of course or which is equal to XAF. Fa naught prime times dxa by minus R minus Ra, and you replace Fa naught prime as R1 plus times Fa naught, and this is the entire volume calculation. So, now let us assume that this process is happening with the help. So, during this process, so there are changes happening into so the volume of the process, volume of the process fluids or even gases are increasing, and also there is an density change. So, in that condition, the XA1 may be evaluated as 1 minus Ca1 by Ca naught divided by 1 plus epsilon A, which is corresponding to the expansion. This is the term that controls expansion Ca1 by Ca naught, and Ca1 would be Fa by V1. Okay, Fa1 would be Fa naught plus Fa3. Fa naught. So, Fa1. Okay, Fa1 would be Fa naught plus Fa3 because these two streams are getting added up, and V1 is V naught plus RVF. So, now we write this in full, Fa naught plus Fa naught into 1 minus XAF, V naught plus V naught plus 1 plus epsilon A XAF. So, solving these two together, we will be able to find out Ca1 as a function of Ca naught 1 plus R minus R XAF divided by 1 plus R plus R epsilon A XAF. And further simplifying this, you will be able to identify XA1 as a function of XAF. Okay, which the what you call the algebraic. So, the pre-multiplication term would be R by R plus 1. So, this is what we need, because if you look at here, your integral is always from XA1 to XAF. So, XA1 to XAF you will write as a function of R by R1 times XAF in this particular equation. So, your eventual equation become V is equal to R plus 1 of integral of XA1 which is equal to R by R1 of XAF times XAF, which is equal to XAF, XA2 which is equal to XAF, which is the final outlet concentration conversion, Fa naught into dxa by minus Ra. So, now again, so this is also helpful in finding out the volume now if you have a recycle reactor, but it is not a clean expression. So, if you have the way we could calculate it, if we have Fa naught into dxa by Ra as an area available, this of course would be an area under the curve, you multiply that with R1, R plus 1. So, if you plot over here, see if your area is the integration is from R by R by R plus 1 times XAF to XAF. So, XAF is the final concentration, let us say this is R XAF by R plus 1, this is that area under the curve, fine. So, and what you need to do here is this is just this part and you need to multiply that with R1. So, the way you may assume this, if you can find out an average height and you assume this as a small rectangle and this is like multiplying that R1 times. So, you may assume that this may be the entire space of that you need to compute as volume. So, this is the integral of R1 R plus 1 times XA1 integral XA1 to XA2 FA naught into dXA by RA, which is saying this is the R1. So, this is that small integral again and you need to multiply that R1 times. So, if you have a intermediate height which is equivalent to, you may assume this as a rectangle, okay, and this is equivalent to one such rectangle, you multiply that R times. So, this is how geometrically we find out the volume of volume, which is of course the key design parameter for any processing. So, we have done it for series series connections of we have individually done it for CSTR and PFR, and we have further done it for the integrated compositions of PF CSTR, two CSTRs in series, two PFRs in series, and combination of CSTR and PFR in with CSTR for coming first and PFR second, and even PFR coming first and CSTR in second, and finally the recycle reactor. So, this kind of culminates the reactor design individually. So, now let us try to seek a concept which is known as so this is see we till this time all our analysis we are fairly looking from the reactor side, but when you are in the field, when you are when we are interested in when we are interested in designing a reaction network system for a particular set of reaction, we will have to shift our focus towards the reaction first, and based on the reaction, what are the most suitable combination of the reactors, be it PFR, be it CSTR, or a combination of those uh, has to be selected. So, attainable region concept is one of that concept that helps you to do it from starting. So, when if you have a reaction, if you have a series of reaction and you need to design a reactor network, you may we may be able to follow the concept of attainable regions. So, okay, so now let us understand what is attainable regions. Attainable region represent the set of all possible states like concentration, temperature, and conversion in a reactor network that can achieve under a given operating conditions and your operational constraints. Operational constraints may also play a key role. So, with suitable algebraic manipulation and mapping the states, attainable region analysis helps the engineers to identify the most efficient reactor design and kind of operational strategies, and this would eventually result in improved process performance and economics. Improved economics essentially mean that the cost effectiveness and as a larger goal of environmental sustainability. So, before the concept of attainable region was developed, optimization and design of the chemical reactors was primarily relied upon traditional methods, that is exploring all possible states and trial and error approaches. So, now let us see how attainable region helps you to do that in a inefficient way. The traditional approach was more prone to missing optimum state and optimum reactor configuration. Of course, it would have given you some results, but it would not have given you the best result. So, attainable region would help you to do that. So, now let us take a symbol. So, that is what, as I told previously, the attainable region analysis would start from the reaction state itself. We are not looking at the reactors at the moment, we are only looking at the reaction. Given this reaction, and the reaction parameters. So, for instance, we need to have a Ca naught. So, 1 kilomole per n power minus 3, and having k1 of all of this, Cb naught, Cc naught, and Cd naught. So, which essentially mean that it is all 0 0 0 here. You start with A and eventually BCD would be formed, having different k values, which is mentioned here. One is of course a reversible reaction, other two are forward reaction. So, given this condition, can you define or develop a reactor network is what we are going to look into. So, the end goal is to determine the reactor configuration that maximizes the production of B, which is over here, for a pure A. So, you are given with a pure A, and A is also doing a side reaction and making D, and B is also going to C, but we are interested in maximizing B. Okay. So, let us see what are the key steps that we need to look into. So, this is a candidate reaction. So, if you need to, so this is again, as I told, this is an example problem statement based on the reactions, side parallel reaction, whatever you have. Okay, you may be able to follow the similar procedures that we elicit here for the reaction networks that we have. So, before we start, let us look at the key aspects. The reaction kinetics was used. So these reaction kinetics were used because they represent a reaction network without an intuitively optimal structure. Because as you may see, A also going to B, and B is of course moving to C, and this A is having a side reaction of going to D, and we are interested in maximizing the production of B. So, it's not very clear from the reaction structure which is what is the best design that we can have. And if you look at individually, a PFR will maximize the amount of B produced in the first reaction, yes, but a CSTR will minimize the amount of A consumed in the second reaction. So, there is conflicting objectives. So, how can we use them together? So, before we move ahead, so we have to choose the fundamental process. So here is what let's start from the basic. In this particular example, the fundamental process is nothing but reaction and mixing. So, mixing. There are two limits in mixing. One is of course a plug flow reactor, other one is continuously stirred tank reactor. So, plug flow reactor is not mixed at all, while the CSTR is extremely well mixed. So, this is the two extreme cases. Fine. So, it is useful to determine the dependence of species concentration on space time of these two environments. So, let us have this particular term called tau, which is the space time. Okay. How can we, so we will do entire analysis based on this space times tau, which is the ratio V by V naught, and we have seen this V by V naught when we defined CSTR, and we also see how CSTR equations can be written in terms of V naught tau. So, that is why I told at that point, let us reserve this term for now, and we will take it up when we do the design of the attainable region. Space time tau is the time necessary to process one reactor volume, and is also called mean residence time or holding time. So, considering the reactions, okay, so we write the PFR equations. PFR would be dCA by d tau minus Kca. C is consumed and B is produced, K plus K2Ca, and of course, and Ca is also doing a side reaction, making D, which is minus K4 Ca square. Let us look at here. Okay, so now coming to the second case, dCb by dt, K K times K1 times Ca and K2 times minus K2 times Cv. This is the addition, and K3 times Cb. Okay, so which essentially mean that you are going as the product C, and dC by d dC by d tau is K3 times Cv only generation, and dC d by d tau is K4 times Ca square. considering that that's the second order process. So now we will be able to rewrite the entire equation in the CSTR case. So CSTR case, we have seen that the process, so this part is of course the rate of the reaction. So we see that Ca minus Ca naught by tau is equal to the rate of the process. So Ca minus Ca naught, let me write Ca is equal to tau times the rate plus Ca naught. So this entire process, when we write it in space time form, this would be fairly an algebraic equations. So let's have both of them together for now, and let's see how do we move further. So now we draw something known as state space diagram. So first case is, so let's start from here. Okay, so this is the plot of concentration of A on the this part of the axis, and concentration of B, which is this part of the axis, as a function of space time. What you may see over here is, okay, A would keep on decreasing, right? Yes, A and B would be generating at certain time, and it would be moving, it would be decomposed or maybe used in again synthesizing Cb. So you would see a peak of B over here, and finally it decreases. Okay, and this is happening in CSTR and PFR also. You see this, sorry, this is happening in PFR and CSTR also. You see a similar profile. Okay, and what you may see here, so the dashed lines represent the CSTR profiles, and the solid line represent the PFR profiles. And here also your C would be continuously decreasing, and your A would be, sorry, B would be, A would be continuously decreasing, and B would reach a maximum, then finally it would decrease. So in state space diagram, you map these points, your CA and CB points together as a single data point, okay, in the curve. So you, in the space you can see that the plot is just between CB and CA, okay, and for a reactor, so for one reactor you would only see one curve, okay. For instance, this particular point would map into this point in the PFR. So the solid line here represent the PFR curve, and the dashed line here represent the CSTR curve. So these two would now map as a single point over here, and the same for the same which for this particular point, okay, which is at the same space time. So you draw at the same space time. So the key aspect here, the space time variable has been eliminated. So you draw at every same space time, you do a lot of vertical lines like this, okay, keep on drawing vertical lines at a given space time. What is the composition concentration of C and CB? For the CSTR case, this would be mapped as a dotted point here. So that's how you generate these two curves. Okay, so now let's see what's happening. So so you can see the behavior is entirely depending upon the change in Ca. So we don't need to analyze the variation of Ca and Cd at the moment. A candidate for the attainable region is identified as the union of the regions contained under the both curves. So it is, so you can see that your solid line, which is of course representing a PFR, has an edge at certain points, okay, and the dashed lines, which is represented by CSTR, has an edge at certain points. So you may see the union of both of them may be can be like a starting point, or what we call it as the candidate attainable region, which is represented by ARC, attainable region candidate. So now the next point is to draw the process vectors. A process vectors define the instantaneous change in the system caused by a fundamental process that is occurring. So okay, if a reaction is only occurring, the reaction vector Ca and Cb will give instantaneous direction, magnitude of change from the current position, and if it's happening mixing, this vector gives the divergence from current concentration based on the new state. So it is the change in terms of the concentration when mixing, and it in terms of rate, it is give you the direction magnitude of change from the current concentration position. So let's assume so let's look at an arbitrary concentration T. And so this dotted line, so dashed line, of course, dashed line is represented by CSTR. So let's this is only the curve of the CSTR from the previous state space diagram. So we replot over here, and let's look at a point T. So T is an arbitrary effluent concentration in the CSTR. We are just using it for demonstration. The vectors can be graphically represented here. Okay, the CSTR rate vector OT is collinear with the feed and the effluent concentration. So this is the vector. So this is the rate vector. And the mixing vector OX. Okay, OX is the linearly connect the current state and the added state. So this is the current state and the added state. So you can see the resulting mixed state lies in this mixing line, and you can compute from lever rule. So what is lever arm rule? Lever arm rule is a method to find out the exact position of mixing point by means of concentration from the mass ratio of the mixing streams. So we will just skip the principle of lever arm rule. This of course part we would have, I hope we would have learned in parts of the mass transfer. So it just says that the exact position of the mixing point, which is somewhere here, you can compute by means of lever arm rule. And from here, this is PFR. So let's assume that you can see here. So at this point, so this is the PFR and this PCSTR, there is a cut. Okay, so the PFR, so whatever you draw tangent to this is the PFR rate vector. Fine. So now so this is a basic analysis, and based on all of this, now let us see how do we do the attainable region. Okay, so the idea here is to draw a process vector to extend the current attainable region. The previous attainable region was what? So previous attainable region was just a union of points. Okay. So we are now looking at this by means of analysis. We are looking at this analysis by means of looking at the mixing. So let's look at a point X. Okay, which is at the boundary point of CSTR curve, a straight line drawn from point O, which is of course right here. You may see over here the straight line drawn from point O to X is the feed. O is the feed point, and X you can draw it. To achieve any concentration along this curve L, you can mix the CSTR output. So here is the CSTR operation, and anywhere you wanted to achieve, you have to add the feed. So which essentially mean that anywhere during this process line, okay, the CSTR outlet of the CSTR operating point is mixed with the feed point O, which essentially means that it is a CSTR with a bypass. Again, you can use lever arm rule to find out wherever you are standing in this line. So notice that when this line is drawn, the concentration candidate region is now extended. It is just not union now. So see, the previously, if you just see that it is just a union, it is only this. Okay. So now what we are trying to say, you draw a line between these two. Okay. So as a result, you are getting some what you call additional operational space here, which we recorded as this. Note that when we draw this line, a candidate region is extended. Okay, when two states mix linearly, mixing can extend this concave region by creating a convex hull. This is of course a concave region, and these are the two endpoints, and eventually it join, and eventually it become a convex hull of the points. And the PFR rate vector, which is at the tangent to the current state, a line tangent to the curve at the point X extends the region above this. Okay. So, and of course, at this point you can find out a PFR profile can be found by numerically solving the PFR balance equation. And how do we eventually reconcile the design now? Okay, at X it's a CSTR, okay, and L if you want to operate over here, course, you would have your own requirements. So if you want to operate over here, it is a CSTR, okay, at a point which is operated with at a point x with a feed bypass, because it is just a mixing, and this side it's a CSTR. At this point it is CSTR, and you have to have a PFR in series, because this curve, the green curve, is corresponding to the PFR in series. So, this attainable region, this part of the attainable region is eventually representing the PFR. So, just to summarize, and finally what is that we need to do is to find the maximum optimal operational point, optimum. So, for in this case, if you see this profile, this is going to be the y, which is the maxima of this function. Okay. So, if you wanted to, let us say if you are interested in maximizing the production of the given species B, so species of B given with a production given with a feed rate of fixed feed rate of A. So, point y is of course the maximum point. You can draw a parallel line to here and figure out what is the corresponding concentration, fine, and how this is operating. And so, at this point, okay, to get this, you need to have a PFR. So, CSTR which is operated at this particular point x, followed by a PFR which is operating at this particular point. So, let us x, this is like 0.4 and this may be possibly 0.18. So, to get y to be maximum, you are looking for uh, a CSTR followed by a PFR. CSTR effluent should come out at 0.4 kilomole per meter cube, and your CSTR effluent concentration, of course, PFR would be at 0.18 at Ca. And you can also compute the corresponding space time, because you have one-to-one mapping between space time and your individual profiles, and you can count. So, that would help you to design your. So, once you have the space time V by V naught, you will be able to find out the volume. This can be determined the corresponding mole balance equation. Also, otherwise you have the individual profile plots available. Okay. So, and you may be able to find out what is the corresponding space time. Once the space time is known, you can, so see, it is as a ratio of V by V naught, you shall be able to find out what is the resulting volume. Okay. So, now in this particular case, this is happening to be 0.037 second and 0.031 second respectively. These are determined by corresponding CSTR and PFR balance equation. So, for instance, let us say you have further constraints. So, this is one attainable region, and if you have a constraint that the concentration of A cannot drop below 0.6. So, which essentially mean that you have to operate here or beyond. So, you cannot operate over here, correct, fine. So, this is corresponding to this point Z. So, what is this? So, you may drop it. So, C is corresponding to, let us say 0.6 kilomole per meter cube, right, and you will have the corresponding CB over here. So, what is this reactor configuration? Any time on this line, this would be a CSTR followed by a bypass of the feed. So, this is how you determine the sequence of combination with which reactor you should place before or after, and what is the corresponding volumes. Okay, so I think these are the key concepts in geometric design of reactors. So, maybe we will just summarize whatever we have learned till now. Okay, we have learned about basic reactor balance, then we have learned about ideal batch reactor design equation. I am not going, so I am not going to read out the expression, it is of course there in your screen, and ideal CSTR rate design equation, and ideal PFR design equation, and eventually a recycle reactor design equation. In all of this, okay, you will be able to find out the corresponding volume by manipulating the variable. So, okay. So, here it is by plotting the Levin spill plot, finding the area of the rectangle, while PFR, it is again plotting the Levens field plot, and due to the integration it is an area under the curve. And recycled reactor, it's slightly more complicated, but you may be able to approximate the area as a rectangle if based on the area under the curve of this particular term multiplied by R1. And qualitatively, we may say that the CSTR offers complete mixing, PFR has no mixing at all, and batch reactor provide mixed contents, while recycle reactor combine partial mixing with recycled streams for enhanced control. And recycle reactor, you can, by tuning the recycle reactor, you can either go to the plug flow regime, or extreme would be the CSTR regime. So, if by controlling the recycle, your recycle reactor may behave like a plug flow in one end and CSTR at the other end. And lastly, we have learned about attainable region concept for analyzing and optimizing chemical reaction. So, it would help you to sequence which reactor should come first, what is the maximum attainable region that you can have, which is it beyond the individual optimal region, and what is the sequence of reactor or what is the type of reactors that is to be used based on the reaction and process condition. Okay. With this, I think I'll complete this particular session, and thank you. We see you soon in the next class. Thanks.